Welcome to another video explaining the universe using the particle model. Well, today's video is another video in this series where I've been covering the diode. In this case, it's the photodiode. These are three of the videos I've shown in the past and recently. The light bulb and the light emitting diode. Although we're covering the photodiode, the LED becomes part of this explanation, and I thought it would be good if you reviewed that. If you haven't seen them, please do so. The last one I did was on the Zener Diode. Now, this is the slide I showed last time that shows three areas where the diode is being used. In the first quadrant, where the voltage is positive here and the current is positive, the signal diode is used for logic circuits and even analog circuits. And last time I talked about the Zener diode, and it uses the Zener breakdown region as its place to function. Today we're going to talk about the photodiode, and this is the region it uses. There's actually a fourth region, which I will go into next time, and that's right here. And the solar diode, or the solar panels that use the diodes, actually operate in this region. Quite interesting how many different ways the diode is being used. Okay, so the function of the photodiode, as described by Wikipedia, is that it's a semiconductor device that converts light into electrical current. The current is generated when photons are absorbed in the photodiode. And as all the other diodes, it can be made with a p-n junction, but in particular, they're often made with a different structure. Not only does it have a p-type region and an n-type region, but in between there's a larger region called the intrinsic region, and that's the area where they claim the current is being generated. Okay, we'll look first at the unit called light intensity, or the lux. The lux is the SI-derived unit of illuminance and luminous emittance, measuring the amount of flux per unit area. So this is an official definition of light intensity, and it is equal to 1 lumen per square meter, and that's shown this additional down here. 1 lux, 1 LX is 1 lumen, which lumen is light bulbs can often be rated in lumens. But this is lumens per square meter, which kind of gives you a sense of intensity. Interesting enough, in photometry, this lux is used as a measure of intensity as perceived by the human eye. So it actually kind of relates it to our own human experience. So that's light intensity. And here's another IV curve, and in this case, you'll see different in this region of the IV curve where the photodiode works. You could have 1,000 lux. That's 1,000 lumens per square meter, and it has a current of approximately 100 microamps. Pretty small, 100, 200, 300, 400 microamps is not a lot of current, but it is there, and the voltages generally applied are from 0 to 5 volts. So this is presumably from the same diode, and if you give it, as you give it more light intensity, you generate more current. The first line, however, is called dark current, and just might as well have been called 0 lux. It's the amount of current flowing when there is no light. And we'll go into that part of the explanation in this video. I'm going to be using this photodiode circuit, and the photodiode is always reverse biased. You have plus voltage tied to the end material, and the negative part of the voltage tied to the positive. That's reversed. Whereas the LED has the positive tied to the P-type material, and the ground eventually gets to the N-type. This is forward biased. This is reverse biased. And I'm going to be using this circuit for further explanation. So let's look at the standard model, dark current, and what the definition of dark current is physically. They're saying this is a physical explanation. Dark current is due to the random generation of electrons and holes within the depletion region of the device. And this is a depletion region. They show it very large to give themselves enough room to explain. Notice it's not only the depletion region or intrinsic region. And the intrinsic region is a large area where it's not doped. It's just a standard a substrate. And of course, the photodiode has a P-type region, and it has an N-type region. And although the people who drew this didn't put in the electric field, it's pretty well known that if you have a positive charge and a negative charge, there is an E field that has a force moving from the P-type to the N-type. Okay, so in the dark current, you have no light coming in. You may have anywhere from 0 to 5 volt voltage. So if you adjust this to 0 and you got no light coming in, they're saying that you've got random generation of electrons and holes in this region, and this E field kind of gets the electrons moving. This diagram shows holes moving the other way. Well, my opinion is holes don't move. They're created they're made when the electron moves away from the atom and leaves the hole. So the electrons move due to the force, and the holes are left behind. And the holes kind of look like they're moving this way, but it's the electron that's moving in this direction. This random generation is probably somewhat thermal. The thermal, you get vibration of all these atoms here, and you may get electrons being freed from their atom. Okay, so but when you actually have light and have a voltage, and that this is the front end of that circuit. So you have light coming in, you have a 5-volt battery. And when you have the light, the photons generate these electron hole pairs and flow around here. So the more light you have, the more pairs are generated and the more current you have. It's a very simple explanation. And so it's not difficult to see how that would happen. But looking at the other end of this circuit, we have an LED, and this is one of my problems with the explanation of light being emitted from a diode. In that video, light emitting diode, I used this picture to explain how the standard model generates a photon, because you have photons coming on. By the way, you got photons coming in, you got photons coming out. But the explanation of how the photon is generated is that a particle, that says particle there, particle hits the atom, it excites it, they say, and an electron moves from one level to the next, and then shortly thereafter it falls down. When it falls down, it releases energy, and the energy is in the form of a photon. If you listen to any of my videos, you understand that my opinion that energy is not real. If it's not real, it can't emit a photon. That's just very, very illogical to me. Now, the particle model, dark current, is just as simple. The only difference between this, again, here, there's no light coming into the diode. If the battery voltage is 0, then you have no G1 particles coming around and through. G1 particles flow in this direction. And so you're just sitting there with a diode and a G2 force field around it, which sets up G2 gravity. And of particular interest is the G1s coming in here lose this G1s, and G1s going this one go this way and lose G1s. In the middle, it's offset a bit because when the N-type has more G1s, it has more loss. It gets to an equal point quicker than this end where you have fewer G1s. At the PN junction or the intrinsic level, this differential. You have a net force moving this way, and you have a lesser force moving that way. It's the equivalent of the electrical field developed by the G2 particle field that surrounds the diode and surrounds all objects. Now, this is what I found is really one of the more interesting structures. This is the PIN structure, the positive type, N type, and in the middle, intrinsic. So here you have the positive P type, the N type, and the intrinsic layer. They have a very wide area where light can be received. And in the particle model, you have G1 particle streams of light with a repetitive pattern coming here. And if you follow the interaction rules, you know that G1 particles can pass right on through. Thing is, light doesn't pass right on through. We all know that. We all cast a shadow while we walk out in the daylight. Light itself doesn't get through, but individual G1 particles can get through, can start here, hit the P type, go through the I, go through the N, and out the diode. So if you think about it here, this is a G1 stream of particles with a repetitive pattern. And if it's white light, it's got multiple patterns, all coming in to the P type, which is here, going through the intrinsic to the N and out. So the light coming from here can move straight. It's not the light, it's the G1 particles that can get through. And so this is, I find this quite interesting that that light has a direct access through the diode to the N-type and the connector and the flow here. What I'm really trying to say is it's not necessarily the splitting of the atom to make electron pair holes. It can be, proposing that it can be an exact flow of G1 particles into the diode at that point. So here is the whole circuit. And I'm going to make a specific point about the battery. Covered this before. The number of particles that a battery adds to the flow of G1s is equal to the voltage of the battery divided by a constant called VG1, the volts per G1. I don't know that number, and I generally assume 0.1. So if you divide 0.1 into 5, then there'll be 50 G1s added at each period of small period of time. But at the same time, the streams of G1 particles hit the photodiode, and it's going to add its A number as well. And that number that the photon is proportional to the number of G1s coming in. I don't know that's an exact statement. I'm saying it's generally proportional to the intensity of this light. We know it's proportional to the intensity In the IV curve where we showed the 1000 lux, 1500, 2000 lux, you can see that the more intense, the more current flows. In the TP model, that means this is adding the equivalent amount it needs for that amount of current. And so when you shine ambient light, sunlight, a flashlight on this photodiode, and you let it stabilize with a continuous set of G1s coming in, you end up with a stable circuit with a base number A of G1 particles flowing through. You have A coming into the battery. You add 50. That's how many you have here. It splits. At this point, this is a connection point where it splits just like it does with a parallel resistor. Some of them go this way, but most of them go that way. The few that go through here, you end up, as the G1s go through, you get G1s here, and you add NP, so you, whatever the value was here, you got more here. So you actually have two sources in this, sources of G1s in this circuit. And when you have enough current, like if dark currents, you don't develop enough voltage to turn the transistor on, but with 1000 lux, you get enough voltage. You need generally 0.7 volts here or higher to turn this on. When this turns on, this is ground down here. The low impedance ground is tied to here. And therefore you have electrons hitting the LED in this direction and causing light, not by electrons jumping up and down and falling and then energy causing photons to be developed. In this case, that base flow, that A part plus the added ones, when they flow through, the vibrating atoms in the diode push out clumps of G1s in a repetitive pattern. And if that pattern is a red pattern, red wavelength, you'll have a red, this is a red LED, you'll have red light coming out. But it's actually random light, white light with a red, white, blue pattern coming in a messy type of mix coming in, G1s coming in, G1s going out. Particle model explanation. In summary, the standard model says it's photons in, photons out, and photons are packets of energy with wave-like properties. TPM explanation is G1s in, G1s out. Simple, straightforward. It's the same thing that I've explained the FM radio transmitter and receiver with antennas. Same things are happening. In fact, the number in here, or I should really say it the other way around, the number being emitted here is proportional to I would think, to the number coming in, making it very much a direct correlation, where electron-hole pairs, eventually, even with a steady state current, electron-hole pairs, are they going to keep generating? In current keep increasing all day long, but don't think that happens. Okay, my name is Bob D. Hilster, and I am your particle model guru. Tune in next time when I'll explain more of the universe using the particle model. Thank you for your attention.